And welcome to Rotational Kinematics, basically the second part of the torque unit. We're going to go over this really fast. Rotational kinematics is the exact same as regular kinematics, except it's rotational. Acceleration becomes rotational acceleration or angular. Delta x becomes delta theta. Like there's a bunch of new variables that are the rotational versions of their linear counterparts or their translational counterparts, and we're just going to go over that. So first, displacement is delta x. This becomes delta theta. Basically, what used to be the difference in position now becomes the difference in angle. And basically this is just in radians. If you use degrees, you're a loser. And this is in meters. The angular displacement is equal to the linear displacement, or delta x over r. All right, next one is velocity. Velocity becomes the omega symbol, which is angular velocity. Basically how fast you're spinning around. This is in meters per second. This is in... Basically, it's radians per second, but we never write the radians because we're all lazy and don't really know what we're doing. And so radians just disappear for some reason because they don't actually exist. It's wild. This is delta x over delta t, or time, displacement over time. This is angular displacement over time. Ooh, yeah. And it's the same thing. It equals v over r. You take the linear and divide it by the radius, but not always, just for these ones. Don't go doing that willy-nilly, that won't work. Then finally we have acceleration. This becomes alpha. Oh geez, that's a bad alpha. I'm a beta male. This is in meters per second squared. This is in just the formula for acceleration, I hope. It's the same thing, but now it's delta velocity angular over time. And oh, you guessed it, it's the exact same thing. You just divide it by the radius. Now, how do I solve one of these problems? The exact same way you would solve a linear one. First, you find context. Is it accelerating or is it constant? Then you draw a picture. I don't really care if you draw a picture. It helps sometimes. I don't know, it's never helped me. Not a visual person. If you're visual, you might want to. Next, you pick your kinematic equation. It's the exact same thing. Okay, let me try to remember what one is. I think this is one, at squared. This is one of your equations, yeah? Switch it out. Literally just put the other ones in. There's no rotational version of time. That would be weird. Time is just, it ascends everything. Yeah, so you swap these bad boys out. You want to make sure that all of your variables are either angular or linear. You can't make this delta x, that would not work. That would be wild. So you have to convert them using the radius. And then you solve it, and then check if it's logical. All right. Boom, boom, boom. Next one, moment of inertia. So when we want to solve force problems, we do F net equals ma, but now we have torque net. What does torque net equal? We know that A becomes alpha. What is this thing? I'll tell you, it's I. This means moment of inertia or rotational inertia. This is inertial mass. This is rotational inertial mass. It's weird. I guess this is translational inertia. This is its resistance to accelerating linearly. This is its resistance to accelerating angularly. What does this equal? It can equal a lot of things. It really depends. If you have a freaking barrel that's going through the center and it's solid, it's gonna have a different moment of inertia than a rod that is rotating around a perpendicular bisector. Wild. There's a table. I'm gonna put it here. I'm gonna do the easy one. Point mass is just a mass rotating around a thing, mr squared. Now, what if you have two masses? Oh, now there's two of them. It's in the middle and they're rotating around it somehow. How would I find the moment of inertia of this whole thing? There's 2 point masses. It's a freaking sum. It's gonna be I of mass 1 plus I of mass 2. Yeah, you just add them. If you got a bunch of barrels or something, I guess you'd add them. I've never seen that before. I mean, it probably exists in the real world somewhere. This is basically how you solve dynamic torque problems. It's pretty cool. You're probably gonna be given a mix of linear and angular variables. You're gonna want to convert them. One problem that I saw that I did not know how to do, and then I did know how to do it, and it was a miracle that I figured it out, was there's this wheel. Yeah, so it's rotating around a center. It's a bike wheel, and you have R1, which is this radius to the inner side of the wheel, and then you got R2 to the outer side of the wheel, and it has a weight of m, and then there's a force that has a radius of this much, and it's going this way. Find the tangential acceleration. This is nuts. I'll show you how to do it. We always start with good torque net equals IA. I forgot what the ring is, what the inertial is for rings. So you'll just have to sub that in yourself. But we have force. There's only one force acting on it, so it's going to be F net times r, which we have 3 r's here. It is the r that the force is at, and that's this one. The key thing is to make sure that your F net, like if you're translating it into T net, torque net, to choose the right radius, the radius that actually like relates to it. Like, oh yeah, it's doing it at a radius of this. How the heck would I solve this? Well, you'd probably solve for alpha first, so you'd like put it all over I, and then the key thing is knowing the different types of acceleration. This is linear, and we know alpha, which is angular, and we also know centripetal. It's centripetal. It's the acceleration towards the center. Next we have radial. These are the same. There is no purpose for this to exist. It is the same. Finally, there's the one that we want to know about, which is tangential. And remember, alpha equals linear acceleration over r, and so A equals alpha times r. This is also the same for tangential. AT equals alpha times r. Yep. So now that I realize, I think these are the same. Yeah, so that should be it. That's all I have. Thank you for watching. Good luck on the test.